Let's take a look at reinforcement learning, another breakthrough in the deep neural networks area. This new technique solves the difficult problem of correlating current action with delayed gratification. It's hard to understand the full impact of a decision you make today in the future. As real life environments are more ambiguous and intangible, reinforcement learning algorithms can be of much use, and this can bring the entire category of artificial intelligence closer to human intelligence. This technique learns to perform a task by trying to maximize the reward it receives for its actions in a specific environment. For example, let's say that there's a simple game of Mario. You have to travel from point A to point B, and in the process, you're gonna get to eat as many apples as you like. And these apples are spread throughout the screen, so you might have to jump, take a left, take a right, and so on. So the algorithm simply tries to learn to play this game by eating as many apples as possible, hence by maximizing its reward. Another serious example could be high frequency trading, where the portfolio makes a decision of a trade and tries to maximize the profit it receives over a set of trades. So these are the terms which you should be clear before we actually look at the architecture. So first we have an agent. So this agent is much like a human being which takes actions which could be A1 through AX. So these are many actions possible within a certain environment. Environment is basically the surrounding in which an agent takes an action. State is the environment at a specific time. Reward is very simple. So if you eat an apple, you get 10 points. If you meet a thorn ball, you get a negative 5 points. Policy is the framework for actions. For example, you could create a policy that to stay away from thorns and to eat more apples. Discount factor, this reduces the value of delayed gratification and encourages immediate gratification. Value V is the long-term value with discount. This basically maps the long-term return of the current state under a policy. So this is the action value or the optimum function cube. This refers to the maximum return of the current state taking action under a certain policy. We have an environment E at a time t, we have an agent A, we have a policy, and we have actions and rewards. Then we also have another environment E1, which is basically iteration of E or the next frame after this state S. So the agent takes a set of actions on the environment at time t. The environment gives back the agent the rewards, and also it moves the agent to the next frame of the environment at t1. So the agent continues the loop of taking action, the environment gives the rewards, and then this loop continues. The policy influences the agent to take actions in a way which maximizes its rewards. It would be beneficial to differentiate between reinforcement learning with supervised and unsupervised learning. Let's take an example of how these different algorithms treat features. In unsupervised learning, the algorithm is trying to find similarities between these features, put them in a certain class. In supervised learning, the algorithm tries to map certain features to a pre-given label. In reinforcement learning, it chooses a certain feature purely based on the reward it brings along with it, irrespective of the similarity it has with other feature or a certain trend. Reinforcement learning technique uses different types of deep learning neural networks. For example, the agent uses an artificial neural net, much like a feed-forward neural network and recurrent neural network. The visual aspect would be processed by a convolutional neural network. Of course, the feedback loop is done through back propagation and so on.